Beneath a shell of ice roughly 18 miles thick, in total darkness, under radiation that would kill a human being in hours, there is an ocean, not a small one. Scientists believe it holds more than twice the volume of every ocean on Earth combined. No sunlight has ever touched it. No instrument has ever sampled it. No camera has ever photographed what lies inside. And yet, in January 2026, NASA confirmed that this ice shell is far thicker than most models had hoped, sealing that ocean away more completely than anyone expected. Europa does not look dangerous. It looks quiet, smooth, almost peaceful. That is exactly what makes it the most unsettling place in the solar system. What is hiding beneath the ice may be the most important question science has ever been afraid to answer. If you find this kind of deep science fascinating, then consider tapping like and subscribe. It genuinely helps this channel keep making content like this, and I appreciate every single one of you who sticks around. Now, with all that being said, are you comfortable? Let's begin. On a clear night in January of 1610, a man in Padua, Italy, pointed a small telescope at Jupiter and noticed something no human being had ever seen before. 3 tiny points of light hovered near the planet, arranged in a line. The next night, they had moved. A few nights later, a 4th appeared. Galileo Galilei had just discovered the 4 largest moons of Jupiter, and in doing so, he shattered a belief that had governed human thinking for more than 1,000 years. Not everything in the heavens revolved around the Earth. Some things revolved around other worlds entirely. Those 4 moons would eventually carry the names of figures from Greek mythology. Io, the volcanic furnace; Ganymede, the largest moon in the solar system; Callisto, ancient and cratered; and Europa, named after a Phoenician princess abducted by Zeus in the old stories. For nearly 4 centuries after Galileo's discovery, Europa remained little more than a dot, a speck of reflected light wobbling around a gas giant 5 times farther from the Sun than Earth. Astronomers could measure its orbit. They could estimate its size. They knew it was slightly smaller than our own moon. But beyond those basic numbers, Europa was a blank. No spacecraft had visited. No close-up image existed. No one had any reason to think Europa was anything more than a frozen, dead ball of ice drifting through the cold outer reaches of the solar system. That impression was not unreasonable. In fact, it was the obvious conclusion based on everything scientists understood at the time. Europa orbits Jupiter at a distance of roughly 480 million miles from the Sun. At that distance, sunlight is roughly 27 times weaker than what reaches Earth. Surface temperatures hover around -260 degrees Fahrenheit. The energy arriving from the Sun is so feeble that it cannot melt anything, cannot drive weather in any meaningful sense, and cannot sustain liquid water on the surface under any known condition. Europa looked, from every available angle, like a place where nothing could possibly happen, and then humanity sent machines to Jupiter. And everything changed. The first real look came in 1979, when NASA's Voyager 1 and Voyager 2 spacecraft flew through the Jupiter system on their way to the outer solar system. They were not designed to study Europa in detail. Jupiter and its radiation environment were the primary targets, and the flybys were brief. But the cameras captured something that immediately made planetary scientists pause. Europa was smooth, strangely, almost unnervingly smooth. While the other Galilean moons displayed the expected pockmarks of billions of years of asteroid and comet impacts, Europa's surface was nearly featureless at large scales. No towering mountains, no deep basins. No ancient, heavily cratered terrain like what covered Callisto or parts of Ganymede. Instead, Europa's face was crisscrossed, with long, thin lines stretching for hundreds of miles across a pale, icy shell. It looked less like a battered moon and more like a cracked eggshell. That smoothness was the first clue. In planetary science, a smooth surface on a solid body means one thing above all others. The surface is young. Impact craters accumulate over time. Every solid body in the solar system that has been sitting unchanged for billions of years is covered in them. The fact that Europa had so few meant something was erasing them. Something was resurfacing the moon, wiping the geological slate clean on a timescale far shorter than the age of the solar system. At the time, no one could say exactly what that process was. Europa remained a mystery, filed away in the growing catalogue of strange outer solar system worlds that deserved a closer look but had no mission dedicated to providing one. What followed was a period of nearly 2 decades, during which Europa existed in a strange scientific limbo. The Voyager data had posed a question that could not be answered without returning to Jupiter, and for a long time, no return was planned. During those years, Europa lived mostly in the minds of planetary scientists who studied the Voyager images frame by frame, debating what the strange surface features might mean. The arguments split roughly along 2 lines. One camp held that the fractured, youthful surface could be explained by processes operating entirely within a solid ice shell. Tidal stresses from Jupiter, they argued, could crack and rework the ice without requiring any liquid water beneath it. The fractures were real, but they were surface deep. Europa might be geologically interesting but internally frozen, a world of ice all the way through, with the cracks driven by the same gravitational flexing that made Io volcanic but expressed differently in a colder, more rigid body. The other camp looked at the same images and saw something more radical. The patterns of disruption on Europa's surface, particularly the regions where large ice blocks appeared to have shifted and rotated like pack ice in an Arctic sea, were difficult to explain without a mobile layer underneath. Solid ice does not behave that way. It does not allow slabs to float, drift, and refreeze in new orientations. Something beneath the surface had to be providing the freedom of movement that the terrain implied. And the most obvious candidate for that something was liquid water. This debate played out across conferences, journal papers, and faculty meetings throughout the 1980s and early 1990s. It was not a fringe discussion. Some of the most respected names in planetary science were involved, and the stakes were understood clearly even then. If Europa had a subsurface ocean, it would become one of the most important astrobiological targets in the solar system overnight. If it did not, it would remain an interesting icy moon, worthy of study but not fundamentally different from dozens of other frozen worlds. The problem was that the existing data could not settle the question. The Voyager cameras had provided images at resolutions of roughly 2 kilometers per pixel at best. At that scale, you could see the broad pattern of fractures and disrupted terrain, but you could not resolve the fine details that might distinguish between a solid ice and liquid water interpretation. The magnetic field data from Voyager was not designed to probe Europa's interior structure, and no other instrument on the spacecraft could provide the measurements needed. What was needed was a dedicated mission to Jupiter, one that would orbit the planet, make repeated close passes of the moons, and carry instruments specifically designed to interrogate their interiors. That mission was Galileo. And its path to launch was anything but straightforward. Galileo was originally planned for a launch in 1982. Technical delays, budget pressures, and the Challenger disaster in 1986 pushed the launch back repeatedly. The spacecraft finally left Earth in October of 1989, but even then, it could not fly directly to Jupiter. It lacked the energy for a straight trajectory and instead performed a series of gravitational assists, swinging past Venus once and Earth twice over the course of 6 years to build up enough speed to reach the outer solar system. Galileo did not arrive at Jupiter until December of 1995, more than a decade and a half after the Voyager flybys had first posed the question it was designed to answer. During those years of waiting, the anticipation in the planetary science community grew steadily. Europa had become something of an obsession for a small but vocal group of researchers who believed the evidence for an ocean was strong enough to warrant serious investigation. The theorists among them had refined models of tidal heating, showing that the gravitational interaction between Jupiter, Io, Europa, and Ganymede could generate enough internal heat to maintain liquid water beneath an ice shell of uncertain thickness. The numbers worked. The physics allowed it. But physics allows many things that do not actually occur in nature, and without direct measurement, the ocean hypothesis remained exactly that. A hypothesis. Galileo changed everything. The magnetometer aboard Galileo detected something during its passes near Europa that could not be explained by the Moon's known composition alone. Europa was generating an induced magnetic field, not a permanent magnetic field like Earth's, driven by a spinning iron core, but an induced one, created by the interaction between Jupiter's powerful rotating magnetosphere and a layer of electrically conductive material inside Europa. The best candidate for that conductive layer, by a significant margin, was saltwater, a global ocean of liquid saltwater hidden beneath the ice. The implications were enormous. This was not a suggestion that Europa might have had water at some point in the distant past, or that trace amounts of moisture might exist in isolated pockets. The magnetic data pointed to a continuous, planet-wide layer of liquid water, an ocean, beneath the ice. Right now, Galileo's camera returned images that supported the interpretation from a completely different angle. The surface of Europa, seen up close, was covered in features that looked remarkably like the fractured sea ice of Earth's Arctic. Vast slabs of ice appeared to have shifted, rotated, and refrozen in new positions. Regions scientists would later name chaos terrain showed areas where the surface had been disrupted, broken apart, and reassembled in patterns consistent with a mobile layer underneath. Long double ridges ran across the surface for hundreds of kilometers, raised features flanking a central crack, consistent with material welling up from below and refreezing along fracture lines. None of these features made sense on a world that was frozen solid all the way through. Every one of them pointed to the same conclusion. Europa's surface was a shell. Beneath it, something was moving. The question that immediately followed was the most obvious one, and also the most difficult. How? How could a moon this far from the sun, this cold on its surface, maintain a liquid ocean underneath? Where was the energy coming from? The answer was Jupiter. Europa does not orbit Jupiter in a perfect circle. Its orbit is slightly elliptical, stretched by the gravitational influence of the other large moons, particularly Io and Ganymede. The 3 innermost Galilean moons exist in what scientists call a Laplace resonance. For every single orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This precise gravitational relationship has persisted for billions of years, and it prevents Europa's orbit from circularizing completely. There is always a slight eccentricity, a slight wobble in the distance between Europa and Jupiter as it goes around. That variation in distance matters because Jupiter is massive. It contains more mass than every other object in the solar system combined, excluding the Sun. When Europa moves closer to Jupiter in its orbit, the gravitational pull intensifies. When it moves farther away, the pull weakens slightly. This rhythmic stretching and relaxing generates friction inside the moon. Rock grinds against rock, ice flexes, the interior heats up. Not from sunlight, Not from radioactive decay alone, though that contributes. From the raw mechanical energy of being gravitationally needed by the largest planet in the solar system, orbit after orbit, for billions of years. Scientists call this process tidal heating. It is the same mechanism that makes Io the most volcanically active body in the solar system. But on Io, the heating is so extreme that it drives eruptions visible from orbit, fountains of sulfur reaching hundreds of kilometers into space. Europa experiences less tidal heating than Io because it orbits farther from Jupiter and the resonance distributes the energy differently. But the heating is sufficient to maintain a global ocean of liquid water beneath the ice shell, insulated from the frozen vacuum above by miles of solid ice acting as a thermal blanket. This is the fundamental picture of Europa that emerged from the Galileo mission and that has been refined, tested, and largely confirmed in the decades since. A moon slightly smaller than Earth's own, an outer shell of water ice. Beneath that shell, a saltwater ocean that may be 60 to 150 kilometers deep. Below the ocean, a rocky mantle and likely a small metallic core. The entire system powered not by the sun, but by the gravitational engine of Jupiter itself. The scientific community recognized almost immediately that this picture had staggering implications. Water, liquid water, is the single most important requirement for life as we understand it. Every living organism on Earth, without exception, depends on liquid water. It is the solvent in which the chemistry of life occurs. Finding a global ocean of it on a moon of Jupiter was not merely interesting. It placed Europa at the very top of the list of places in the solar system where extraterrestrial life might exist. But the word might is doing critical work in that sentence. And understanding why requires looking more carefully at what Europa actually is, rather than what we hope it might be. Because here is the part of the story that often gets lost in the excitement. Europa is not Earth. It is not even close to Earth. The ocean beneath its ice exists in conditions so radically different from anything on our planet that calling it an ocean at all risks creating a false sense of familiarity. The water is real. The saltwater chemistry appears to be real. But everything else about this environment is alien in ways that are difficult to fully appreciate without slowing down and considering what it would actually mean to be there. Start with the darkness. Europa's ocean has never seen sunlight. Not once. Not in 4.5 billion years. The ice above is miles thick, and even if it were thinner, the distance from the sun means the light arriving at Europa's surface is already desperately faint. Beneath the ice, there is no light at all. 0 photons. The ocean exists in a darkness so complete that it is not merely the absence of light, it is the permanent, structural impossibility of light. No sunrise will ever reach it. No photon from any star will ever penetrate to where the water begins. On Earth, the deep ocean is dark too. Below roughly 1,000 meters, sunlight fades to nothing, and the creatures that live there exist in perpetual night. But even the deepest trenches on Earth sit beneath an atmosphere connected to a sunlit surface. Energy from the sun drives the global ocean circulation. Organic material sinks from the sunlit upper layers and feeds the deep ecosystems below. The entire deep ocean of Earth is, in a very real sense, still connected to the star above. Europa's ocean has no such connection. The ice shell is not a thin barrier through which energy leaks. It is a massive insulating layer, kilometers thick, cutting the ocean off from the already meager sunlight that reaches the surface. Whatever energy exists in that ocean comes from below, from the interior, from tidal heating acting on the rocky mantle underneath. And even that energy source, as recent research has shown, may be far weaker than scientists had hoped. Consider the pressure. Europa's ocean, if it reaches the depths that models suggest, would exert pressures at the seafloor comparable to or exceeding those found in the deepest trenches on Earth. Europa's ocean could be 60 kilometers deep or more. Even accounting for Europa's lower gravity, roughly 1/7 of Earth's, the pressure at the seafloor would reach hundreds of atmospheres, comparable to or exceeding the conditions found at the deepest points in Earth's oceans. This is not a shallow pool. It is a deep, pressurized, lightless volume of water on a scale that dwarfs anything on our planet. And then there is the isolation. Europa's ocean is not accessible. It is not exposed. There are no coastlines, no beaches, no open water anywhere on the surface. The entire ocean is sealed beneath a shell of ice that, based on the most recent measurements, averages approximately 29 kilometers thick in the region observed by Juno. That is roughly 18 miles of solid, rigid, frozen water between the surface and the liquid below. 18 miles. The cruising altitude of a commercial airliner is roughly 6 to 7 miles. Stack nearly 3 of those on top of each other, and you begin to approach the thickness of Europa's ice shell. That shell is not just a passive barrier, it is geologically active in its own right. The fractures, ridges, and chaos terrain visible on the surface are evidence that the ice moves, cracks, shifts, and reforms over time. But these processes operate at the surface and in the upper layers of the shell. The connection between the surface and the deep ocean is, based on current evidence, extremely limited. The cracks and pores detected by Juno's microwave radiometer extend only hundreds of feet below the surface, nowhere near deep enough to provide a continuous pathway through the full thickness of the shell. This means Europa's ocean is, to a first approximation, a sealed environment. Material from the surface does not easily reach the water. Material from the ocean does not easily reach the surface. The two domains, the irradiated, fractured ice above and the dark, pressurized ocean below, exist in a state of profound separation, connected only through slow, indirect processes that scientists are still working to understand. That separation is one of the most important facts about Europa, and it is one that often gets underemphasized in popular discussions. When people talk about Europa as a candidate for life, the conversation tends to focus on the presence of water. Water is there, therefore life might be there. But water alone is not sufficient. Life, at minimum, requires water, energy, and chemistry. The energy question on Europa is deeply uncertain. The chemistry question depends on what reaches the ocean from above and what the ocean generates from below. And the ice shell stands between those two sources of input like a wall 18 miles high. This is the picture of Europa that existed as of the early 2020s, a world of extraordinary scientific interest. A moon that hides a global ocean beneath its surface, a place that combines water, possible energy, and possible chemistry in a configuration that no other body in the solar system replicates at this scale. And simultaneously, a place so sealed, so dark, so cold on the outside, and so inaccessible on the inside, that actually determining what exists beneath the ice remains one of the most formidable challenges in the history of space exploration. But the story did not stop there. Because between 2024 and 2026, a series of findings landed that changed the picture again. Not by overturning it, by sharpening it. By replacing hopeful ambiguity with hard numbers. And some of those numbers were not what the scientific community wanted to hear. In late 2024, data from Juno's 22 flyby of Europa was presented at the American Geophysical Union meeting. The headline finding was the ice shell thickness, measured for the first time using a microwave radiometer that could peer beneath the surface and measure temperatures at depth. The number that came back was approximately 35 kilometers of rigid conductive ice in the initial presentation, later refined to 29 kilometers plus or minus 10 in the peer-reviewed paper published in Nature Astronomy in December 2025. Either way, the results supported the thick shell model and dealt a blow to the thin shell scenarios that had been more optimistic for habitability. A thick shell means a longer route for any chemical exchange between the surface and the fond. Ocean. It means less heat escaping from the interior. It means a world that is more sealed, more insulated, and more cut off from the processes that could deliver the oxidants and nutrients that life might need. Around the same time, separate modeling studies, presented at conferences and later published in early 2026, concluded that Europa's seafloor is likely geologically quiet today. The tidal forces acting on the rocky interior, while sufficient to keep the ocean liquid, do not appear strong enough to drive significant faulting, volcanism, or hydrothermal activity at the ocean floor. Paul Byrne, the planetary scientist at Washington University in St. Louis, who led one of these studies, put it plainly: the energy does not seem to be there to support life, at least today. Earlier, Juno data had also suggested that Jupiter's radiation produces less oxygen at Europa's surface than previous estimates, further reducing the expected supply of one key ingredient that might eventually make its way into the ocean and the plumes. For years, scientists had hoped that Europa might be venting material from its ocean into space, the way Saturn's moon Enceladus does through dramatic geysers at its south pole. If Europa had plumes, a spacecraft could fly through them and sample ocean material without ever landing or drilling. The Hubble Space Telescope reported tentative detections of plume activity in 2012 and 2016. But subsequent observations, including searches with the James Webb Space Telescope, have failed to confirm active plumes. The evidence remains ambiguous at best. Taken together, these findings painted a more sobering portrait of Europa than the one that had dominated popular science coverage for years. The ocean is real. The ice is thick. The sea floor may be quiet. The surface chemistry exchange is limited. The plumes are unconfirmed. The moon remains one of the most scientifically important targets in the solar system, but the pathway from interesting to habitable had become considerably narrower and more uncertain. And yet, even as these results dampened some of the more optimistic scenarios, they did something else simultaneously, something that matters more for the story this script is telling. They made Europa more unsettling. Because a Europa with a thin ice shell, active plumes, vigorous hydrothermal vents, and easy chemical exchange would have been a Europa that is potentially accessible. Challenging to explore, certainly, but within the reach of missions that could fly through plume material, analyze surface deposits, and infer ocean conditions from relatively straightforward measurements. The Europa that the data now describes is different. It is a world that is more closed, more sealed, more completely hidden. An ocean that may or may not harbor conditions relevant to life, locked beneath a shell of ice so thick and so rigid that no mission currently planned or even seriously proposed will directly access it. A seafloor that may or may not be active, lying at the bottom of an ocean so deep and so dark that even imagining a probe reaching it requires technology that does not yet exist. This is the Europa that the latest science has revealed. Not a world that is less interesting, a world that is more unknowable, a world that holds its secrets tighter than any place humanity has ever tried to study, and that is what makes it so deeply, fundamentally unsettling. Not the danger on the surface, though the danger is real and extreme. Not the possibility of life below, though that possibility remains scientifically legitimate. What makes Europa unlike anything else in the solar system is the combination. A vast ocean exists beneath the ice. It may contain conditions partially recognizable from our own planet's deep-sea environments. And it is sealed away behind a barrier so thick, so cold, and so radiation-blasted on the outside that reaching it may be beyond the capacity of any mission this century. Europa does not advertise its secrets. It does not erupt. It does not glow. It does not send obvious signals. It simply sits there, orbiting Jupiter every 3.5 days, its pale, cracked surface reflecting a fraction of the feeble sunlight that reaches it, giving almost nothing away. What lies beneath that surface is the subject of everything that follows. And the deeper we go, the stranger and more frightening the picture becomes. Imagine you could stand on Europa. Set aside for a moment every engineering impossibility that would need to be solved to get you there. Ignore the years of travel through interplanetary space, the radiation shielding, the landing system, the life support. Just picture yourself standing on the surface, boots on the ice, looking around. The first thing you would notice is the sky. Jupiter dominates it. The planet hangs overhead roughly 24 times larger in apparent diameter than the full moon appears from Earth. It does not look like a distant object, it looks like a wall. A swirling, banded wall of ochre and cream and rust, streaked with storms larger than entire planets. The great red spot alone, if it happened to be facing you, would appear as a bruise on that wall, roughly the width of Earth itself. Jupiter does not set and rise the way the Sun does, from our perspective. Europa is tidally locked to Jupiter, meaning the same hemisphere always faces the planet. If you landed on the Jupiter-facing side, the gas giant would be permanently fixed in your sky, rotating slowly on its axis, its cloud bands churning in real time, never moving from its position above the horizon. The second thing you would notice is the light, or rather, the lack of it. Europa receives roughly 1/25 the sunlight that Earth does. At that distance from the Sun, our star appears noticeably smaller and dimmer than it does from home. It still provides enough illumination to see by, roughly equivalent to an overcast afternoon on Earth, but the quality of the light is different. The shadows are longer. The contrast is lower. The warmth that sunlight carries on Earth is entirely absent. Standing in direct sunlight on Europa, your skin would feel nothing. The photons arrive, but they carry so little energy across that vast distance that they cannot meaningfully warm anything. The surface temperature around you sits at approximately -260 degrees Fahrenheit, roughly -160 degrees Celsius. At these temperatures, the ice beneath your feet is harder than granite. Water ice at these conditions does not behave like the slippery, crackable material you know from frozen lakes on Earth. It becomes a rock, a mineral, a structural material as rigid and unyielding as the stone in a mountain. The ground beneath you would be pale, almost white in some places, with faint streaks of tan and reddish-brown material tracing lines across the surface in every direction. Those lines are Europa's most iconic surface feature, visible even from orbit. They are called lineae, and they stretch for hundreds, sometimes thousands of kilometers across the moon's face. From your vantage point on the surface, they would not look like the clean, sharp lines you see in spacecraft images. They would look like low ridges, sometimes just a few hundred meters across, flanking a central trough. Some would rise tens of meters above the surrounding terrain. Others would be barely noticeable, subtle undulations in the ice that you might walk across without realizing their significance. But their significance is enormous. Those ridges and fractures are the visible scars of a world that is being pulled apart and pushed back together by forces operating deep below the surface. Europa's ice shell is not static. It moves, it cracks, It shifts, and the patterns of that movement are written across every square kilometer of the surface in a language that planetary scientists have spent decades learning to read. The double ridges are among the most studied features. These are parallel raised lines flanking a central crack, often running for hundreds of kilometers in gently curving arcs. On Earth, no natural ice formation looks quite like them. The leading explanation involves a process where tidal stresses open a fracture in the ice. Warm material from below wells up into the crack, freezes, and builds up ridges on either side as the crack repeatedly opens and closes with each orbital cycle. Some models suggest that liquid water or warm convecting ice exists just beneath these ridges, close enough to the surface to influence the terrain above. In 2022, a study published in Nature Communications drew a striking comparison. Researchers found that double ridges on Europa bear a remarkable structural resemblance to features observed over a shallow water sill in northwest Greenland's ice sheet. The Greenland ridges formed when subsurface water refroze and pressurized, fracturing and lifting the ice above. If the same mechanism operates on Europa, it implies that pockets of liquid water may exist within the ice shell itself, not just in the deep ocean far below, but embedded within the ice at relatively shallow depths. These would not be connected to the main ocean. They would be isolated lenses or sills of water trapped within the shell, possibly containing their own chemistry, their own pressure conditions, their own frozen isolation. Then there are the chaos regions. These are areas where the surface appears to have been shattered, jumbled, and refrozen into a disordered mosaic of ice blocks. The most famous, Connemara Chaos, looks like a jigsaw puzzle that has been broken apart and reassembled with pieces missing and others rotated at odd angles. Rafts of older surface material float within a matrix of newer, smoother ice, as if an area of the shell partially melted or collapsed and then refroze around the surviving fragments. Chaos terrain covers a significant fraction of Europa's surface. Its formation requires a mechanism capable of disrupting the ice from below, either through localized heating, convective upwelling in the ice shell, or the influence of warm material rising from deeper within the moon. The scale of some chaos regions is enormous. Thera Macula and Thrace Macula, two large chaos features in the southern hemisphere, each span areas comparable to the Great Lakes. Whatever process creates these disruptions operates with enough energy to rework ice over areas of thousands of square kilometers. The surface also shows evidence of something called band formation. Bands are zones where the ice shell has pulled apart and new material has filled the gap, similar to seafloor spreading at mid-ocean ridges on Earth. The older ice on either side of a band can sometimes be matched up like pieces of a torn photograph, confirming that the surface was once continuous and has since been separated by the intrusion of fresh ice from below. This is, in a loose but physically meaningful sense, a form of plate tectonics. Not the kind driven by mantle convection beneath silicate plates, as on Earth, but an icy analog where the ice shell fractures, separates, and reforms in response to forces from below. All of these features, the ridges, the chaos regions, the bands, the fractures, tell the same story. Europa's surface is young and geologically active. Crater counts suggest the average age of the surface is somewhere between 40 million and 90 million years. In geological terms, that is yesterday. It means that the processes reshaping the ice are not ancient relics of a more energetic past. They are ongoing. Europa is alive in a geological sense, continually reworking its outer shell, even as the ocean below remains sealed beneath it. But the images of fractures and chaos terrain, as striking as they are, can create a misleading impression. They are still photographs. They are snapshots frozen in time. They show the results of activity, without conveying the activity itself. And the activity on Europa is not something that happened once and stopped. It is happening right now, continuously, on a schedule dictated by the Moon's orbit around Jupiter. To understand what Europa's surface is actually like as a physical environment, you need to understand what tidal flexing does to the ice shell in real time, every single orbit, endlessly. Europa completes one orbit around Jupiter every 3.5 Earth days. During that orbit, its distance from the planet varies because the orbit is slightly elliptical, maintained in that shape by the gravitational resonance with Io and Ganymede. When Europa swings closer to Jupiter at its nearest approach, the gravitational pull intensifies. The planet's enormous mass reaches into the Moon and physically deforms it, stretching the body along the line, connecting it to Jupiter and compressing it in the perpendicular direction. When Europa moves to the farthest point in its orbit, the pull relaxes slightly and the deformation eases. The result is that Europa's entire shape changes, subtly but measurably, every 3.5 days. The ice shell, the ocean, and the rocky interior all participate in this deformation. At the surface, the ice may rise and fall by up to approximately 30 meters over the course of each orbital cycle, according to models that assume a liquid ocean beneath the shell. 30 meters. That is roughly the height of a 10-story building. The ground beneath your feet, if you were standing on Europa, would be rising and falling by that amount every few days. Not in a single dramatic event, not as an earthquake or a convulsion, but as a slow, rhythmic, continuous flexion driven by the relentless pull of the largest planet in the solar system. You would not feel it in the way you feel an earthquake on Earth. The motion is too slow, spread across hours rather than seconds. But the ice feels it. 30 meters of vertical displacement distributed across a shell thousands of kilometers wide translates into enormous mechanical stresses. The ice is being bent, stretched, compressed, and released on a schedule that never stops. Every 3.5 days, for billions of years, without pause, without relief. Without any mechanism to absorb the stress other than cracking, shifting, and deforming. This is why the fractures exist. This is why they are everywhere. The lineae, the double ridges, the bands, the chaos terrain, all of them are the surface expression of an ice shell being mechanically worked by tidal forces on a timescale that is, by geological standards, astonishingly rapid. The fractures are not ancient wounds that healed long ago. Many of them are active. They open and close with each orbit. Material wells up into them when they gape and is squeezed out or frozen when they close. The double ridges grow incrementally, orbit by orbit, as the cycle repeats. The surface is not a static landscape. It is a machine, flexing on a 3.5-day cycle, driven by the gravitational engine overhead. If you could listen, and if sound could travel through Europa's vanishingly thin atmosphere, you might hear it. The deep, slow groaning of ice under stress. The sharp crack of a new fracture propagating across the surface at the speed of sound in solid ice. The subtle grinding of blocks shifting against each other along existing fault lines. On Earth, researchers studying ice sheets in Antarctica and Greenland have recorded the sounds of glacial ice under tidal stress, and the recordings are haunting. Low-frequency moans and pops and creaks that sound almost biological, almost as if the ice were alive and in pain. Europa's ice shell, under far greater tidal stress than anything on Earth, would produce its own version of these sounds, inaudible to any human ear, but real, physical, continuous. The surface is not quiet. It is working, straining, breaking and reforming in an endless cycle of deformation that has been running since the Moon first settled into its orbital resonance billions of years ago. This tidal flexing is the reason the surface looks the way it does. But it is also the reason the surface is so hostile to anything that might try to exist on it, or to any machine that might try to land there. The ground is not stable, it moves. Not quickly enough to throw you off your feet, but relentlessly enough that any structure placed on the surface would be subjected to continuous mechanical stress. Over days and weeks, the repeated flexing would fatigue materials, open gaps in seals, and work at any joint or connection point. The surface of Europa is not just cold and irradiated. It is mechanically restless, a platform that never stops moving, driven by forces that no engineering can counteract. But even this relentless tidal flexing is not the most hostile aspect of Europa's surface. That distinction belongs to something invisible, silent, and relentless. Something that does not crack the ice or shift the terrain, but instead attacks the very molecular structure of anything exposed to it. Jupiter's radiation environment. Jupiter possesses the most powerful magnetic field of any planet in the solar system. It is roughly 20,000 times stronger than Earth's and extends outward in a vast magnetosphere that engulfs all 4 Galilean moons. This magnetosphere traps enormous populations of charged particles, primarily electrons and protons, accelerating them to tremendous energies as they spiral along magnetic field lines. Europa orbits deep within this magnetosphere. It is embedded in a radiation environment so intense that it would be lethal to any unshielded biological organism within hours. The ionizing radiation dose at Europa's surface is equivalent to approximately 5.4 sieverts per Earth day. To put that number in context, a dose of 1 sievert is enough to cause noticeable radiation sickness in a human being. A dose of 5 sieverts delivered over a short period is considered potentially fatal without medical intervention. On Europa, you would accumulate that dose every single day, not from a single event. Not from a solar flare or a nuclear accident, from the steady, constant, unrelenting bombardment of charged particles streaming through Jupiter's magnetosphere and slamming into the surface. The radiation does not arrive uniformly. Mapping studies using data from the Galileo spacecraft and Voyager electron measurements have shown that the harshest radiation is concentrated in zones around Europa's equatorial region, forming oval-shaped bands that cover more than half the Moon's surface. The trailing hemisphere, the side that faces into the oncoming flow of magnetospheric particles as Europa orbits Jupiter, receives significantly higher doses than the leading hemisphere. Near the poles, radiation levels drop somewhat, but nowhere on the surface is truly safe by biological standards. This radiation does not merely threaten hypothetical astronauts, it actively transforms Europa's surface chemistry. When high-energy electrons and ions strike the ice, they break apart water molecules through a process called radiolysis. The fragments recombine into new compounds, including molecular oxygen, hydrogen peroxide, and various sulfur-bearing molecules, delivered to the surface by material ejected from Io. Over geological timescales, this radiation-driven chemistry has processed the upper meters of Europa's ice into a complex mixture of compounds that did not exist when the ice first formed. This has a dual significance. On one hand, the radiation creates oxidants, molecules that could serve as chemical energy sources for life if they were somehow transported to the ocean below. On the other hand, the radiation destroys any complex organic molecules or potential biosignatures that might have been brought to the surface from the ocean. If material from the deep ocean were deposited on Europa's surface through cracks or eruptions, the radiation would begin to degrade it almost immediately. Studies have estimated that biosignatures, such as amino acids, would be destroyed within the upper 10 to 20 centimeters of ice in the highest radiation zones. Any search for signs of life on Europa's surface would need to dig below this radiation-processed layer to find material that has not been chemically altered beyond recognition. The practical consequence for exploration is severe. A lander on Europa's surface would need to carry enough radiation shielding to protect its electronics from the relentless particle bombardment. It would need to drill or scrape past the radiation-processed surface layer to reach ice that might preserve original ocean chemistry. And it would need to do all of this on a world where the surface temperature makes lubricants freeze solid, metals become brittle, and mechanical systems face engineering challenges that no previous space mission has had to confront at this scale. This is the environment that any future mission to Europa must survive, not for years, not even for months in most proposed scenarios. Current lander concepts envision surface operations lasting days to weeks at most before radiation damage accumulates to mission-ending levels. The surface of Europa is not a place where machines linger. It is a place where machines endure, briefly, before the environment destroys them. And then there is the ice itself, not as a geological feature, but as a barrier. The results published in December 2025 and January 2026 from Juno's microwave radiometer brought the thickness of Europa's ice shell into sharper focus than ever before. The measurement indicated a rigid conductive ice layer averaging approximately 29 kilometers thick, roughly 18 miles, in the region Juno observed. If a warmer convective layer exists beneath that rigid shell, the total ice thickness could be even greater. If dissolved salts are present, the estimate might decrease by roughly 5 kilometers, but even in the most optimistic interpretation, the shell remains formidably thick. 29 kilometers of ice. To visualize what that means, consider that Mount Everest rises approximately 8.8 kilometers above sea level. Stack more than 3 Everests on top of each other, and you approach the thickness of Europa's ice shell. The deepest borehole ever drilled on Earth, the Kola superdeep borehole in Russia, reached approximately 12.2 kilometers before engineers were forced to stop because temperatures at that depth exceeded what the drilling equipment could withstand. Europa's ice shell is more than twice that depth. And unlike the rock of the Kola Peninsula, Europa's ice becomes harder and more resistant to mechanical penetration at the temperatures found in the outer solar system. The Juno data also revealed that the near-surface ice contains irregularities, small cracks, pores, and voids, estimated to be no larger than a few centimeters in diameter, extending to depths of hundreds of feet. These scatterers were initially a source of interest, because they might represent pathways for material exchange between the surface and deeper layers. But the Juno measurements indicate that these features are shallow. They do not extend anywhere close to the base of the ice shell. They are surface layer phenomena, not conduits to the ocean. This finding has significant implications for one of the most debated questions about Europa. How does material move between the surface and the ocean? The surface is bathed in radiation that creates chemically interesting compounds. The ocean below may need those compounds to support any potential biology. But the ice between them is enormous, rigid, and apparently lacks the continuous fracture networks that some earlier models had proposed. The January 2026 study from Washington University in St. Louis added another layer to this picture. Paul Byrne and colleagues modeled the tidal stresses acting on Europa's rocky interior and concluded that the forces are unlikely to drive significant geological activity at the seafloor today. No active faulting. No hydrothermal vent systems of the kind found along mid-ocean ridges on Earth. The tidal heating that keeps the ocean liquid appears to be operating at a level sufficient to prevent freezing, but insufficient to drive the kind of vigorous geological processes that create energy-rich environments at the bottom of the ocean. This is a crucial finding, because for years, the default assumption in many habitability discussions was that Europa's seafloor would resemble the hydrothermal systems found in Earth's deep oceans. On Earth, hydrothermal vents support entire ecosystems in total darkness, powered by the chemical energy released when superheated water reacts with fresh rock. These vents were considered a plausible analogue for what might exist on Europa's ocean floor. If hot water was circulating through cracks in Europa's rocky mantle, it could provide the energy gradients and chemical nutrients necessary for life. The 2026 modeling results suggest that this scenario may not apply. Europa likely has some internal heating, enough to maintain a liquid ocean, but the seafloor itself may be geologically quiet. No volcanism shooting through the ice, as occurs on neighboring Io. No significant fracturing or faulting at the rock-water interface. The ocean floor may be a cold, still, dark expanse of rock, with limited interaction between the water above and the silicates below. This does not definitively rule out habitability. As we will see, alternative energy sources have been proposed that do not depend on seafloor activity, but it does change the picture substantially. The default optimistic scenario, a Europa with an active seafloor feeding energy and chemistry into a liquid ocean that exchanges material with the surface through cracks and plumes, has been replaced by something more sobering. A Europa with a thick, rigid ice shell, a geologically quiet seafloor, limited surface-to-ocean exchange, and no confirmed plumes venting ocean material into space. And yet, even this more constrained picture does not diminish the fundamental strangeness of what Europa represents. Because the ocean is still there, the water is still liquid, the moon is still being heated by Jupiter's gravity, and the ice shell, for all its thickness, is not perfectly static. The surface features prove that the shell moves, cracks, and reshapes itself over geological timescales. Something is happening inside this moon, even if the details remain frustratingly beyond reach. Consider the chaos regions again. The formation of Connemara chaos and similar features requires localized disruption of the ice shell from below. Whether this involves convective plumes of warm ice rising through the shell, pockets of subsurface water melting through, or some other mechanism, it requires energy input at specific locations that exceeds the background level. The ice shell is not uniformly dead. It has active zones, places where the barrier between surface and interior temporarily weakens, where material from deeper layers may reach the surface or come close to it. Some researchers have proposed that these chaos regions might represent the closest thing Europa has to windows into the ocean below. Not open windows, not gaps in the ice, but zones where the shell is thinner or more disrupted, where the separation between the frozen surface and the liquid interior is reduced. If a future lander could target one of these regions and drill through a locally thinned section of ice, the distance to the ocean might be significantly less than the 18-mile average. But even a locally thinned ice shell on Europa is likely to be kilometers thick. The engineering challenge of drilling through multiple kilometers of ice in a radiation environment that limits surface operations to days or weeks, using a spacecraft that must carry all of its power and equipment from Earth across 500 million miles of space, remains beyond any technology that currently exists or is currently funded for development. This is the reality of Europa's surface. It is not merely cold. It is not merely dark. It is not merely irradiated. It is not merely mechanically restless, flexing under tidal forces every 3.5 days. It is all of those things simultaneously, combined with a physical barrier of ice so thick that accessing what lies beneath it represents one of the greatest engineering challenges humanity has ever contemplated. And the surface is the part of Europa we can see. The part we have images of, the part where spacecraft have already flown and instruments have already measured. Everything that follows, everything about the ocean, the seafloor, the chemistry, the energy sources, the question of whether anything lives in that darkness, is inference. It is modeling. It is educated estimation based on magnetic field data, surface composition, gravitational measurements, and analogy with environments on Earth. No human eye has ever seen Europa's ocean. No instrument has ever touched it. No sample has ever been collected from it. We know it is there because the evidence is overwhelming and consistent across multiple independent lines of measurement. But we know almost nothing about what it is like, its temperature profile, its exact salinity, its currents, if it has any, its pressure structure, the composition of its seafloor, whether anything dissolved in it absorbs or emits light, whether anything moves through it. All of that is hidden. All of it lies beneath the surface we have just described, a surface that repels investigation with radiation, punishes machinery with cold, flexes under gravitational forces that never relent, and seals away its interior behind a wall of ice wider than most mountain ranges on Earth are tall. The surface of Europa is a warning. It says, in every way that physics allows, that what lies below is not meant to be easily found. And yet, the surface itself, cracked and fractured and chaotically reworked, also whispers that something below is worth finding. That contradiction between a surface that conceals and a surface that hints, between a world that seals itself shut and a world that cannot quite hide the evidence of what it contains, is what makes Europa unlike any other place in the solar system. It is not the deadest moon. It is not the most violent. It is not the most extreme in any single category. It is the most secretive, the most closed, the most frustratingly, tantalizingly sealed. And beneath that seal, in darkness so total that the word loses its ordinary meaning, lies an environment that scientists believe may hold some of the most consequential answers in the history of biology. What that environment might actually look like, what recent science suggests about its energy sources and chemistry, and why even the most cautious estimates of what exists down there are enough to change how we think about life in the universe, is where we turn next. Go back to that image of standing on Europa's surface. You are on the ice. Jupiter fills the sky. The radiation is silent and invisible, but relentless, tearing apart molecules in the ice around you at a rate your body could not survive for a single day. Now imagine you could pass through the ice. Not drill through it, not melt your way down, but simply sink through it like a ghost, descending through the shell at a steady rate. Watching the environment change around you as you go deeper. For the first few hundred feet, you would pass through ice that has been processed by radiation. This is the uppermost skin of the shell, where charged particles from Jupiter's magnetosphere have broken water molecules apart and recombined them into new compounds: hydrogen peroxide, sulfur dioxide, molecular oxygen, carbon dioxide. The ice in this layer is not pure. It is chemically altered, stained with the byproducts of billions of years of bombardment. Below that, the radiation's influence fades. The ice becomes cleaner, purer, colder. The temperature at the surface is roughly -260 degrees Fahrenheit, and it stays brutally cold for a long way down. At these temperatures, the ice is as hard as bedrock. It does not flex. It does not flow. It simply sits there, rigid, crystalline, motionless, on any timescale a human being could perceive. You keep descending, kilometer after kilometer, mile after mile. The ice remains solid, remains cold, remains dark. There is no sound, no vibration, no sense of anything happening. Just ice, extending in every direction, above you and below you and around you, a frozen volume so vast that it contains more solid water than any glacier system on Earth. But at some point, something begins to change. The temperature rises, not quickly, not dramatically, but measurably. The deeper you go, the warmer the ice becomes, heated from below by the tidal energy that Jupiter's gravity pumps into Europa's interior. The rigid, conductive upper shell that Juno measured gives way, gradually, to ice that is slightly warmer, slightly softer. Some models suggest that at sufficient depth, the ice enters a convective regime, where it is warm enough to flow very slowly, like the glacial ice in Earth's ice sheets, churning in sluggish, overturning cells that transport heat upward from the base of the shell toward the colder surface above. And then, somewhere between 15 and 35 kilometers below the surface, depending on the model, depending on the salt content, depending on assumptions about the internal heat flow, you reach a boundary. The ice ends, and something else begins. Water, liquid water. Dark, cold by terrestrial ocean standards, but warm enough to remain unfrozen, salty, pressurized. Extending downward for perhaps another 60 to 150 kilometers before reaching the rocky seafloor below. This is Europa's ocean, and from here on, almost everything we say about it is inference. We know the ocean exists. The evidence from Galileo's magnetometer, which detected the induced magnetic field signature of a global conductive layer, remains one of the most robust measurements in planetary science. Independent analyses of Europa's gravitational response to Jupiter's tidal forces, measured through subtle variations in the Moon's orbital motion, support the presence of a liquid layer consistent in depth and density with a saltwater ocean. The surface geology, the fractures, the chaos terrain, the double ridges, all point to a mobile layer beneath the shell. Multiple independent lines of evidence converge on the same conclusion. There is an ocean under the ice. We know the ocean is large. Current estimates suggest it contains somewhere between 2 and 3 times the volume of all of Earth's oceans combined. Europa itself is smaller than our Moon, roughly 3,100 kilometers in diameter, but the ocean wraps the entire Moon in a continuous shell of liquid water. There are no continents interrupting it, no land masses dividing it into separate basins. It is one ocean, global in extent, touching every point on the underside of the ice shell and every point on the surface of the rocky interior below. We know the ocean is salty. The conductivity required to generate the observed induced magnetic field implies dissolved ions, most likely sodium chloride, common table salt, along with magnesium sulfate and possibly other salts. Observations by the Hubble Space Telescope and ground-based spectroscopy have identified what appears to be sodium chloride on Europa's surface, concentrated in geologically young regions where material may have relatively recently been deposited from below. In 2019, researchers using the Hubble detected a spectral feature at 450 nanometers consistent with irradiated sodium chloride crystals, strengthening the case that Europa's ocean chemistry includes the same dominant salt found in Earth's seas. We know the ocean is dark, in the most absolute sense that word can carry, as we described earlier. But the significance of that darkness changes when considered alongside the ocean's other properties. No bioluminescence has been detected from orbit, nor could it be with current instruments, even if it existed. Whatever processes occur in that water, chemical or otherwise, occur without any photon of external illumination, and have done so since the ocean formed, potentially billions of years ago. And that is roughly where confirmed knowledge ends and informed speculation begins. Because almost everything else about Europa's ocean, its temperature profile, its current systems, its chemical composition below the level of bulk salinity, the state of its sea floor, and, above all, whether anything lives in it, remains unknown. Start with the temperature. The ocean must be above the freezing point of its particular brine composition, or it would not be liquid. For a saltwater solution with the concentrations that models suggest, that freezing point is slightly below 0 degrees Celsius. But how much above freezing the bulk ocean sits is uncertain. Some models predict an ocean that is cold throughout, hovering just a few degrees above its freezing point, with minimal temperature gradients from top to bottom. Others suggest that tidal heating in the rocky interior could create warmer zones near the seafloor, generating at least modest temperature differences that might drive very slow convective circulation. The question of circulation matters enormously. On Earth, ocean currents distribute heat, nutrients, and dissolved gases across the entire ocean system. The global thermohaline circulation, driven by differences in temperature and salinity, connects the surface waters of the tropics with the deep waters of the polar regions in a cycle that takes roughly 1,000 years to complete. This circulation is critical for maintaining habitable conditions across a wide range of marine environments. Europa's ocean has no surface exposure and no sunlight-driven temperature gradients to power circulation in the way Earth's system works. Any currents that exist would be driven by different mechanisms. Tidal forces from Jupiter could generate tidal currents, rhythmic flows driven by the varying gravitational pull as Europa moves through its slightly elliptical orbit. These would be relatively slow but persistent, operating on Europa's 3.5-day orbital period. Heat from the interior, if concentrated in certain regions, could drive thermal convection cells, with warmer water rising and cooler water sinking. And if ice melts or freezes at the base of the shell, the resulting freshwater or brine rejection could create salinity-driven flows. Modeling studies have explored all of these possibilities. The results vary widely depending on the assumed heat flux from the interior, the salinity structure, and the thickness of the ice shell. Some models produce vigorous circulation patterns with jets and eddies reminiscent of terrestrial ocean dynamics. Others predict a sluggish, nearly stagnant ocean with minimal mixing. The truth is that without direct measurement, we simply do not know which picture is closer to reality. Now, consider the seafloor. This is the boundary between Europa's ocean and its rocky mantle, the place where water meets silicate rock, and where, on Earth, some of the most extraordinary ecosystems in the deep ocean thrive without any input from the sun. For years, the default assumption among astrobiologists was that Europa's seafloor would host hydrothermal activity. The reasoning was straightforward. Tidal heating warms Europa's interior. Some of that heat must escape through the rocky mantle into the ocean. On Earth, where similar heat escapes through the oceanic crust, the result is hydrothermal vents, fissures in the seafloor where superheated water laden with dissolved minerals jets into the surrounding ocean. These vents support entire ecosystems, communities of organisms that derive their energy not from sunlight, but from the chemical disequilibrium between the hot, mineral-rich vent fluid and the cold, oxygen-bearing deep water around it. The discovery of hydrothermal vent ecosystems on Earth in 1977 was itself a revolution in biology. It proved that life could thrive in conditions previously considered impossible, in total darkness, under crushing pressure, at temperatures ranging from near freezing to above boiling, sustained entirely by chemical energy from the planet's interior. The analogy to Europa was irresistible. If similar vents existed on Europa's seafloor, they could provide both the energy and the chemical nutrients necessary for life. But the 2026 study from Washington University in St. Louis challenged this analogy directly. Byrne and colleagues modeled the tidal stresses acting on Europa's rocky interior using updated estimates of the Moon's internal structure and the forces generated by its orbital resonance with Io and Ganymede. Their conclusion was stark. The tidal forces are likely insufficient to drive significant geological activity at the seafloor today. No active faulting, no volcanic eruptions, no vigorous hydrothermal circulation. This does not mean the seafloor is completely inert. Some level of heat must still be escaping from the interior, or the ocean would freeze. But the heat flux may be diffuse, spread evenly across the seafloor rather than concentrated at localized vents. A diffuse heat source produces a very different environment from a concentrated one. Instead of dramatic chimneys jetting superheated water into the ocean, the seafloor would be a cold, dark plain where warmth seeps upward so gradually that it barely registers against the background temperature of the ocean above. Byrne himself acknowledged the significance of this finding, while noting that it is one study, not the final word. But combined with the Juno ice shell measurements and the lack of confirmed plumes, the picture of Europa's interior energy budget has shifted in a direction that reduces confidence in the most optimistic habitability scenarios. And then, just weeks after the quiet seafloor study was published, two separate findings pushed the conversation in a different direction. Not by overturning the bad news, but by offering alternative pathways that did not depend on the assumptions that had just been weakened. The first came from a researcher named Douglas Truong, who presented results at the American Geophysical Union meeting and published work proposing that radioactive decay of elements within Europa's ocean itself could provide a significant energy source for life. The idea was inspired by extreme environments on Earth, deep mines and sediment layers far from any hydrothermal system, where microbial communities survive on energy derived from the radioactive breakdown of uranium, thorium, and potassium in surrounding rocks. Truong and his colleagues modeled the concentrations of three radioactive isotopes, uranium-235, uranium-238, and potassium-40, that might be present in Europa's ocean based on studies of meteorites and comparisons with the compositions of Earth and Enceladus. These isotopes, if they leached from Europa's rocky mantle into the ocean over geological timescales, would undergo natural radioactive decay in the water itself. That decay releases energy, splitting water molecules into hydrogen and oxygen ions through a process called radiolysis. Microorganisms, if they existed, could harvest the energy carried by these ions, essentially feeding on radiation chemistry without needing a volcanic vent or any other concentrated energy source. The elegance of this hypothesis is that it decouples habitability from seafloor geology. Even if Europa's seafloor is as quiet as the Byrne study suggests, radioactive elements would still be present in the rock. They would still dissolve into the water, they would still decay. And they would still produce energy. The process is slow and diffuse, but it operates everywhere the ocean contacts rock, which on Europa means across the entire seafloor surface of a global ocean. Kevin Trin, a planetary scientist at the California Institute of Technology, described the idea as opening up new possibilities for sustaining a biosphere because it does not require life to exist near the seafloor specifically. The energy would be distributed throughout the water column, potentially supporting organisms at any depth rather than confining them to localized vent sites. This is not a confirmation that life exists in Europa's ocean. It is a demonstration that one of the key objections, the apparent lack of concentrated energy sources, may not be as fatal to habitability as the quiet seafloor results initially suggested. The universe of possible energy pathways on Europa is wider than the hydrothermal vent model alone. The second finding came from a completely different direction, not from below, but from above. Austin Green and Catherine Cooper at Washington State University published a study in the Planetary Science Journal in January 2026 examining whether chemical nutrients created by radiation at Europa's surface could make their way through the ice shell to the ocean below. The mechanism they proposed is called crustal delamination, a process borrowed from Earth geology where dense material at the base of a tectonic plate peels away and sinks into the mantle below. On Europa, the analogous process would work like this. Jupiter's radiation bombards the surface ice, interacting with salts and other materials to create chemical compounds, oxidants, sulfur-bearing molecules, and other products of radiolysis. Over time, this radiation-processed ice becomes denser than the clean ice below it, particularly as salts concentrate in certain regions through geological processes at the surface. When the density contrast becomes large enough, and when tectonic forces in the ice shell provide the mechanical impetus, chunks of this dense, nutrient-rich surface ice could detach and sink downward through the shell. The researchers' models showed that under a range of plausible conditions, this material would sink all the way through the ice shell and eventually detach into the ocean itself, delivering a payload of chemically interesting compounds from the irradiated surface to the liquid water below. This is significant because it provides a mechanism for connecting two environments that the thick ice shell otherwise keeps separate. The surface chemistry, driven by Jupiter's radiation, creates oxidants and other reactive molecules. The ocean below may contain reductants, chemical species that would react with those oxidants to release energy. If the two can be brought together, the resulting chemical disequilibrium could power biological processes. On Earth, the energy that drives most life comes ultimately from chemical disequilibrium, the difference between oxidized and reduced chemical species. Photosynthesis creates this disequilibrium at the surface by using sunlight to split water. Hydrothermal vents created at the sea floor by releasing reduced chemicals into oxidized ocean water. On Europa, crustal delamination could create it by delivering surface oxidants into an ocean that has been accumulating reduced compounds from its rocky interior for billions of years. Green described the idea as novel in planetary science, but inspired by a well-understood process in Earth science. The key finding from their models was that the process works across a range of conditions. It does not require a specific ice shell thickness or a specific salt concentration. It operates wherever the surface ice has become dense enough relative to the ice below it, and wherever the shell experiences the kind of tectonic activity that Europa's surface clearly demonstrates. Together, these two findings, radioactive decay as an energy source within the ocean and crustal delamination as a nutrient delivery mechanism from the surface, do not prove that Europa is habitable. They do something more subtle and in some ways more important. They demonstrate that the recent discouraging results about ice thickness and seafloor geology do not close the door on habitability. They narrow certain pathways while revealing others. The picture becomes more complex, more nuanced, and in a strange way, more unsettling, because it suggests that the question of life on Europa cannot be settled from a distance. It requires going there. And going there, as we have already described, is extraordinarily difficult. There is one more piece of the ocean puzzle that deserves attention. In 2023, observations from the James Webb Space Telescope identified carbon dioxide on Europa's surface, concentrated in a region called Terra Regio. Terra Regio is a chaos terrain feature, one of those disrupted zones where the ice shell appears to have been broken apart and refrozen. The carbon dioxide detected there showed isotopic and spatial characteristics consistent with an origin from the ocean below rather than from external sources like comets or meteoritic material. Carbon is one of the fundamental elements of life as we understand it. Every biological molecule on Earth, every protein, every strand of DNA, every lipid membrane is built on a carbon backbone. Finding carbon dioxide on Europa's surface that appears to have come from the ocean suggests that carbon chemistry is occurring in the water below. It does not prove biological activity. Carbon dioxide can be produced by purely geological and chemical processes with no involvement from living systems. But it confirms that the ocean is not a simple vat of salt water. It contains dissolved carbon compounds, which means the chemical palette available for potential biology is richer than just water and salt. The carbon dioxide detection also provides indirect evidence that material from the ocean can reach the surface. At least in certain locations and over geological timescales, this contradicts the most pessimistic interpretation of the thick shell results, which might suggest total isolation between the ocean and the surface. Terra Regio shows that the barrier is not absolute. Exchange occurs, slowly, locally, imperfectly, but it occurs. The ocean is not completely cut off. It communicates with the surface, whispering chemical messages through the ice in places where the shell has been disrupted. To understand what makes Europa's ocean uniquely unsettling, it helps to compare it with the only other confirmed ocean world that has been studied in comparable detail. Enceladus, a tiny moon of Saturn roughly 500 kilometers across, roughly 1/7 the diameter of Europa. Enceladus became the darling of astrobiology in 2005 when NASA's Cassini spacecraft discovered enormous plumes of water, vapor, and ice particles erupting from fractures near the moon's south pole. These geysers, shooting material hundreds of kilometers into space, were immediately recognized as a direct window into the moon's interior. Cassini flew through the plumes multiple times, sampling their contents with its mass spectrometer. The results were remarkable. The plumes contained water, salts, silica nanoparticles consistent with hydrothermal activity at the seafloor, molecular hydrogen that could serve as a chemical energy source, and complex organic molecules with masses exceeding 200 atomic mass units. In short, Enceladus handed scientists almost everything they could ask for. Confirmed plumes, confirmed ocean material accessible from space, confirmed hydrothermal chemistry at the seafloor, confirmed organics. A moon that was practically advertising its habitability, spraying the evidence into space for any passing spacecraft to collect. Europa offers none of this. Its plumes, if they exist at all, have never been confirmed despite repeated searches. Its ocean material has never been directly sampled. Its seafloor chemistry has never been measured. Everything we know about Europa's interior comes from indirect measurements, magnetic fields, gravity data, surface composition, and modeling. Where Enceladus opens its doors and invites investigation, Europa locks them shut. And yet, Europa's ocean is vastly more significant in at least one critical respect: scale. Enceladus's ocean is now believed to be global, like Europa's, but it is far thinner and the moon itself is dramatically smaller, meaning its total water volume is a small fraction of Europa's. Europa's ocean wraps the entire moon. It contains more than twice the water of every ocean on Earth combined. If life exists in both oceans, Europa's biosphere, if it has one, would be operating in an environment orders of magnitude larger than anything on Enceladus. The size of the ocean matters because it affects everything from chemical cycling to the long-term stability of habitable conditions. A larger ocean has more thermal inertia, more chemical buffering capacity, more space for gradients and niches. It can sustain conditions over longer timescales with less vulnerability to disruption. If you are looking for a place where life could not only begin but persist for billions of years, accumulating complexity and filling ecological niches in total darkness. Europa's ocean is the most compelling candidate in the solar system, but the very features that make Europa's ocean scientifically superior also make it scientifically inaccessible. Enceladus practically begs to be studied. A future mission could fly through its plumes and potentially detect biosignatures without ever touching the surface. Europa demands that you come to it, that you survive the radiation, that you land on the ice, that you drill through 18 miles of frozen armor, that you enter an ocean no instrument has ever touched. The contrast between the two moons crystallizes what makes Europa so uniquely disturbing. Enceladus is the accessible ocean world, smaller, less significant in absolute terms, but generous with its secrets. Europa is the significant ocean world, larger, older, more promising in scope, but closed, sealed, silent, offering almost nothing to the observer who cannot break through the shell. There is one more terrestrial analogy that sharpens the picture further. Beneath the East Antarctic ice sheet, roughly 4 kilometers below the surface, lies Lake Vostok, the largest subglacial lake on Earth. Sealed beneath the ice for an estimated 15 to 25 million years, Lake Vostok exists in permanent darkness, under enormous pressure, isolated from the atmosphere and the surface biosphere above. When Russian scientists drilled down to the lake's surface in 2012, after more than 2 decades of effort, they found water that had been cut off from the rest of the planet for millions of years. The discovery of microbial life in subglacial Antarctic environments, including in Lake Vostok's accretion ice and in other sub-ice lakes across Antarctica, transformed the scientific community's understanding of where life can persist. Organisms were found surviving in conditions of extreme cold, extreme isolation, and near-total nutrient deprivation, sustained by chemical interactions between the water and the underlying rock. These were not thriving ecosystems by any surface standard. They were sparse, slow metabolizing communities, eking out an existence in one of the most inhospitable environments on Earth. But they were alive. And they had been alive, sealed under the ice, for longer than the entire genus Homo has existed. The parallels to Europa are immediate and powerful. If microbial life can persist beneath 4 kilometers of ice on Earth for millions of years, then a similar persistence beneath Europa's ice shell, which is thicker but has been in place for far longer, is not physically implausible. The Antarctic sub-ice lakes are not perfect analogues. They exist on a planet with an active biosphere above, and some level of contamination or connection to the surface cannot be entirely ruled out. Europa's ocean has no such connection. Whatever exists there, if anything exists there, has been on its own for the entire history of the solar system. But the lesson from Vostok and its sister lakes is not that Europa definitely has life. It is that the conditions we once considered incompatible with biology, permanent darkness, extreme cold, total isolation, immense pressure, are not incompatible at all. Life on Earth has demonstrated repeatedly and in progressively more extreme environments that it can survive wherever liquid water and a minimal energy source coexist. The barriers we thought were walls turned out to be doors, at least on this planet. Whether those doors open on other worlds is the question that Europa poses more sharply than any other destination in the solar system. Now step back and consider what we have assembled. An ocean more than twice the volume of all of Earth's oceans. Saltwater, likely containing sodium chloride and magnesium sulfate. Carbon chemistry confirmed by surface detections. Potential energy from radioactive decay distributed throughout the water. Potential nutrient delivery from the radiation process surface through crustal delamination. A seafloor that may be quiet but is not proven to be entirely inert. subglacial environments on Earth that demonstrate microbial survival under superficially similar conditions of cold, dark isolation. And an ice shell that, despite its thickness, shows evidence of exchange with the ocean below in specific disrupted regions. This is not a guaranteed recipe for life. It is a set of conditions that, if they occurred together on Earth, would almost certainly support microbial ecosystems. On our planet, wherever liquid water, chemical energy, and the right elements come together, life appears. There is no known exception. From boiling hot springs to frozen Antarctic lakes, from the crushing depths of the Mariana Trench to the acid-soaked walls of abandoned mines, wherever the basic requirements are met, life fills the niche. Whether that principle extends beyond Earth is the single most important unanswered question in biology, and Europa is the place where that question is most sharply posed. Not because it is the most likely candidate for life. Enceladus, with its confirmed plumes, its detected organics, and its demonstrated hydrothermal chemistry, offers a more immediately testable target. But Enceladus is small. Its ocean is regional. Its total water volume is a fraction of Europa's. Europa's ocean is an entirely different scale. A global, deep, ancient body of saltwater that has persisted for potentially billions of years. If life exists in Europa's ocean, it has had an almost inconceivable amount of time to develop. The ocean may have been present for nearly as long as Europa itself has existed, roughly 4.5 billion years. On Earth, the earliest evidence of life appears in rocks approximately 3.5 to 4 billion years old. Life on our planet arose quickly, geologically speaking, once conditions became suitable. If the same principle holds elsewhere, and if Europa's ocean has provided suitable conditions for even a fraction of its history, then the time available for biological processes to begin is measured in billions of years. What form such life might take is entirely speculative. There is no basis for imagining complex organisms, no reason to envision fish or anything remotely resembling animal life. If anything exists in Europa's ocean, it is overwhelmingly likely to be microbial, single-celled organisms adapted to extreme cold, extreme pressure, total darkness, and whatever chemical energy sources the environment provides. It would be life at its most fundamental, its most stripped down, its most alien by terrestrial standards, and yet its most universally significant. Because confirming the existence of even a single microbial cell in Europa's ocean would be, without exaggeration, one of the most consequential discoveries in the entire history of science. It would mean that life is not unique to Earth, that the chemistry of living systems can emerge independently in environments radically different from the one where we first evolved, that the universe is not biologically empty, but biologically active, potentially teeming with organisms in oceans beneath ice shells, on moons orbiting gas giants, around countless stars across the galaxy. That possibility is simultaneously exhilarating and deeply unsettling. And the unsettling part is not the life itself. It is the fact that it may be there, right now, in an ocean we know exists, on a moon we can see through a backyard telescope, and we cannot reach it. We cannot sample it, we cannot test for it, we cannot confirm or deny it with any technology we currently possess. The ocean is there, the conditions may be there, the time has been there. And the answer is locked beneath 18 miles of ice in the darkness around Jupiter, as inaccessible to us as the interior of a sealed vault buried at the bottom of the sea. That inaccessibility is not a temporary inconvenience. It is not a problem that will be solved by the next mission or the one after that. It is a fundamental feature of what Europa is. The ocean exists in a place that the universe has made extraordinarily difficult to reach. And that difficulty, That sealed, hidden, unknowable quality is what transforms Europa from a scientific curiosity into something genuinely frightening. Not frightening in the way that a supernova is frightening, or a black hole, or a gamma-ray burst. Those are dangers that announce themselves. They radiate energy across the electromagnetic spectrum. They are visible, measurable, comprehensible in their violence. Europa is frightening in a quieter, deeper way. It is frightening because it may contain something profoundly important, and it refuses to let us see it. On October 14th, 2024, a Falcon Heavy rocket lifted off from Kennedy Space Center in Florida, carrying the largest spacecraft NASA had ever built for a planetary mission. Europa Clipper, a machine the size of a basketball court with its solar arrays fully deployed, began a journey of 1.8 billion miles toward Jupiter. It will arrive in April of 2030. When it gets there, it will not land on Europa, it will not touch the ice, it will not drill, it will not deploy a submarine or lower a probe into the ocean. It will fly past, again and again, 49 times, skimming as close as 16 miles above the surface at its lowest passes, gathering data with 9 scientific instruments and a gravity experiment, and then pulling away each time into the relative safety of a wider orbit around Jupiter to escape the worst of the radiation. That is the mission. 49 flybys. Each one lasting only minutes in the closest approach phase, because lingering near Europa means accumulating radiation damage that would eventually kill the spacecraft's electronics. The total time Europa Clipper will spend within close range of the Moon across its entire multi-year mission is measured in hours, not days, not weeks, hours. Scattered across 49 separate encounters, each carefully planned to cover different regions of the surface and subsurface. Europa Clipper carries an ice-penetrating radar called Reason that will send radio waves into the ice shell and listen for reflections from subsurface boundaries, potentially detecting the ice-ocean interface or any pockets of liquid water embedded within the shell itself. It carries a magnetometer that will measure the induced magnetic field in far greater detail than Galileo could, tightening the constraints on the ocean's depth, salinity, and extent. It carries spectrometers that will map the chemical composition of the surface, identifying regions where ocean material may have been deposited. It carries cameras that will image the surface at resolutions fine enough to identify individual boulders. The mission is extraordinary in its scope and ambition. It represents decades of scientific advocacy, engineering development, and a total investment exceeding $5 billion. It is, by any reasonable measure, one of the most important robotic missions ever launched. And here is the strange, uncomfortable truth about what it will likely accomplish. Clipper's data will almost certainly make the mystery of Europa more agonizing, not less. Consider what the instruments are designed to return. The ice-penetrating radar may map the underside of the shell with enough resolution to reveal its topography, the shape of the boundary between ice and ocean, the contours of a ceiling that no eye has ever seen. The magnetometer may narrow the salinity of the ocean to a specific range, telling us not just that the water is salty, but how salty, constraining the chemistry with a precision that transforms a vague idea into a concrete environment. The spectrometers may identify specific organic compounds on the surface, molecules that could only have originated from the ocean below, deposited in chaos regions where the shell was disrupted, preserved in patches that the radiation has not yet fully destroyed. Each of these measurements will make Europa's ocean feel more real, more specific, more like a place rather than an abstraction. Scientists will be able to describe the ocean's depth to within a meaningful margin. They will be able to estimate its composition with genuine confidence. They will be able to point to specific locations on the surface and say, "This material came from the water below." and none of it will tell them whether anything is alive down there. The data will bring us closer to the door than humanity has ever been. It will let us press our ear against the surface and listen with instruments of exquisite sensitivity. It may let us hear the structure of the lock, feel the shape of the keyhole, even detect faint chemical whispers seeping through the cracks. But the door will remain closed. The ocean will remain unseeable, untouchable, unsampled. We will know more about the cage than any previous generation of scientists could have imagined knowing. And we will still not be able to see what is inside it. There is a particular kind of frustration that comes from better information about something you cannot reach. It is not the frustration of ignorance. It is the frustration of proximity, of knowing that you are close, that the answer may be right there, that the data is pointing in a direction that screams significance, and that the final step, the one that would settle everything, remains beyond your capability. Clipper may deliver exactly this kind of frustration in the highest possible resolution to an entire generation of planetary scientists. That is the mission's likely legacy. Not an answer, a sharper question. A more detailed portrait of a world that refuses to reveal its deepest secret. And the knowledge that to go further will require something far more ambitious, far more expensive, and far more technologically daring than anything humanity has ever attempted in space. What would the next step be? In concept studies and white papers, the answer has taken several forms. A lander that would touch down on Europa's surface, survive the radiation long enough to analyze ice samples from the top few centimeters or meters, and search for biosignatures preserved in the radiation-processed surface layer. This concept was studied in detail by NASA's Jet Propulsion Laboratory. The engineering challenges are immense. The lander would need to function autonomously in an environment where communication delays with Earth average roughly 80 to 90 minutes round trip and can exceed 100 minutes. It would need radiation shielding sufficient to protect its instruments for a surface lifetime measured in days. It would need a sampling system capable of drilling or scraping through ice harder than granite at temperatures where most mechanical systems become brittle and unreliable. And it would need to perform chemical analysis of unprecedented sensitivity, searching for organic molecules at concentrations that might be vanishingly small in radiation-blasted surface ice. Even this ambitious concept would only scratch the surface, literally. A lander could tell us what the top layer of ice contains. It could potentially detect biosignatures that have been transported from the ocean and partially preserved in the ice, but it could not reach the ocean itself. The ocean lies kilometers below, beyond the reach of any drill a lander could carry. The true dream, the mission that would definitively answer the question, is something that does not yet exist, even as a funded concept study. A cryobot, a nuclear-powered, self-sterilizing, autonomously navigating probe capable of melting or drilling through the entire thickness of Europa's ice shell, entering the ocean, and operating as a submersible in total darkness at crushing pressures with no real-time communication with Earth, searching for signs of life in an environment that no human-built machine has ever encountered. The engineering requirements for such a mission border on science fiction. The probe would need to carry enough energy to melt through roughly 18 miles of ice. It would need to maintain structural integrity under pressures that increase continuously during descent. It would need to prevent contamination of the ocean with terrestrial organisms, a planetary protection requirement of extraordinary stringency. Because introducing Earth microbes into Europa's ocean would compromise the very discovery the mission was designed to make. It would need to communicate through the ice shell, either by trailing a cable, which introduces catastrophic failure risks over an 18-mile length, or by deploying relay transmitters at intervals during descent, or by some other method that does not currently exist. And once it reached the ocean, the probe would need to navigate, sense, and analyze an environment about which it would know almost nothing in advance. The ocean's temperature, chemistry, current patterns, and pressure structure would all be unknowns until the probe encountered them directly. It would be operating in permanent darkness, unable to use optical sensors in any meaningful way unless it carried its own light source, and even then, the range of visibility in a possibly murky, particle-laden ocean might be measured in meters. Researchers at institutions, including NASA's Jet Propulsion Laboratory, the Applied Physics Laboratory at Johns Hopkins University, and the Woods Hole Oceanographic Institution, have worked on early-stage concepts for such probes, drawing on experience with under-ice operations in Earth's polar regions. Prototype cryobots have been tested in glaciers and ice sheets on Earth, melting through ice using heated tips and communicating via fiber optic tethers. These tests have been valuable, but the gap between drilling through a few hundred meters of terrestrial glacier ice and penetrating 18 miles of ice on a moon orbiting Jupiter is not a matter of incremental improvement. It is a matter of multiple, simultaneous, technological revolutions. The most optimistic timelines for a Europa cryobot mission place it decades in the future, well into the second half of this century. And those timelines assume sustained funding, political will, and technological breakthroughs that are by no means guaranteed. In the interim, the ocean remains sealed. This is the reality that the scientific community confronts when it talks about Europa. The most important question, is there life in the ocean, cannot currently be answered. The tools required to answer it do not exist. The mission architectures that could carry those tools have not been funded. And the environment where the answer resides is among the most inaccessible in the solar system. Now consider what that means not just scientifically, but as a fact about the universe we inhabit. Humanity has walked on the moon. We have driven robots across the surface of Mars. We have landed a probe on Titan, the largest moon of Saturn. We have visited comets, asteroids, and dwarf planets. We have sent machines to the edge of interstellar space. In every one of these cases, the challenge was enormous, but the target was accessible in principle. The surface was there. You could see it, photograph it, touch it, sample it. Europa is different. Europa has a surface, and we can reach it, barely, with extreme difficulty, for brief periods. But the thing that makes Europa important, the ocean, is not on the surface. It is inside, locked away, hidden behind a physical barrier of ice that is wider than most nations are tall, in an environment so hostile that even the most hardened spacecraft can only survive there for days. There is no other place in the solar system that presents this specific combination of extreme scientific importance and extreme physical inaccessibility. Mars may or may not have had life in the past, but its surface is open, exposed, and increasingly well explored. Enceladus vents its ocean material directly into space through plumes that a spacecraft could fly through and sample without landing. Titan has a thick atmosphere and hydrocarbon lakes that are challenging but ultimately reachable. Europa alone offers the possibility of a vast, ancient, potentially life-bearing ocean that we can infer from the outside, but cannot directly access with any technology that currently exists. That gap between what we know and what we can reach is the source of Europa's unique psychological power. It is not the radiation. It is not the cold. It is not even the possibility of life, taken alone. It is the combination of all of these things with the knowledge that the answer may be right there, beneath the ice, and we cannot get to it. Think about what that does to the human imagination. We are a species that explores. We cross oceans, we climb mountains, we build telescopes to see galaxies billions of light years away. We send robots to other planets. The act of reaching, of looking, of going where we have not been before is so fundamental to what we are that it is woven into every culture, every civilization, every era of human history. And Europa says no, not forever, perhaps, but for now and for the foreseeable future. Europa holds its secret behind a wall we cannot breach. The ocean is there. The water is liquid, the chemistry may be right, the energy may be sufficient, the time has been more than enough, and we cannot look, we cannot check. We cannot open the door. That is not a comfortable feeling. It is, in a very specific and deeply human way, terrifying. Not the terror of immediate danger, not the terror of a predator or a catastrophe. The terror of a locked room. The terror of knowing that something important may be inside, that you can hear the faintest sounds through the walls, that every indirect measurement suggests the room is not empty, and that the lock cannot be picked with any tool you possess. There is a comparison that scientists sometimes make when discussing Europa, and it is worth examining because it reveals something about how we relate to the unknown. People often compare Europa to Earth's deep ocean. The similarities are real. Both environments exist in total darkness. Both involve liquid water under enormous pressure. Both are cut off from sunlight. Both may support life through chemical energy rather than photosynthesis. On Earth, hydrothermal vent ecosystems were not discovered until 1977. For the entire history of biology before that year, scientists assumed that all life on Earth ultimately depended on the sun. The discovery that entire ecosystems could thrive in total darkness, powered by the planet's internal heat, was a revolution that reshaped our understanding of where life can exist. The comparison to Europa is obvious. If Earth's deep ocean can support life in darkness and pressure, perhaps Europa's ocean can too. But the comparison conceals a crucial difference. Earth's deep ocean is accessible. We have visited it. We have sent submersibles to the bottom of the Mariana Trench. We have deployed remotely operated vehicles that spend months at a time documenting vent ecosystems. We have collected samples, sequenced genomes, and built a detailed understanding of how deep-sea life works. The deep ocean was unknown for centuries, but once we developed the technology to reach it, the mystery resolved quickly. Europa does not offer that resolution. Europa's ocean is not merely deep. It is sealed. The barrier is not water depth, but ice thickness. And the ice is not in our own backyard, reachable by a ship and a submersible launched from a coastal port. It is on a moon orbiting the largest planet in the solar system, 500 million miles away, bathed in radiation that would kill any unshielded human in hours. The deep ocean comparison makes Europa feel familiar. It makes the problem feel solvable, as if we just need a better submarine. But the truth is that Europa's ocean is in a fundamentally different category of inaccessibility. It is not hard to reach in the way that the bottom of the Mariana Trench was hard to reach in 1950. It is hard to reach in the way that the interior of a planet is hard to reach. The barrier is not depth alone. It is a shell of solid material, miles thick, on a world where every aspect of the environment works against the machines we would need to send, and yet the scientific community continues to plan, continues to study, continues to develop concepts for missions that might, decades from now, make the first direct contact with Europa's ocean. The Europa Clipper will arrive in 2030. ESA's Jupiter Icy Moons Explorer, JUICE, launched in April 2023 and will arrive in the Jupiter system in 2031, studying Ganymede primarily, but also making flybys of Europa. The data from both missions will be combined to build the most complete picture of Europa's ice shell and ocean yet achieved. The Woods Hole Oceanographic Institution, selected by NASA in late 2025 to lead a 5-year research project called Investigating Ocean Worlds, will spend the years while Clipper is in transit developing better techniques for analyzing organic molecules that might be detected by future missions. Their work explicitly prepares for the possibility that Europa Clipper will detect chemical signatures that demand follow-up, signatures that might be consistent with biological activity, but that cannot be confirmed without direct sampling. This is the posture of a scientific community that knows the answer may be within reach, but not within grasp. Not yet. The preparations being made now are preparations for a future in which the technology catches up with the ambition, in which a cryobot becomes feasible, gets funded, gets built, gets launched, survives the journey, survives the radiation, melts through the ice, and reaches the water. If that day comes, what will it find? Nobody knows. That is not a hedge. That is not scientific caution substituting for genuine uncertainty. Nobody knows. The range of possibilities spans from an ocean that is chemically interesting but completely lifeless, a vast body of sterile saltwater that has remained biologically empty for 4.5 billion years, to an ocean that supports a microbial biosphere so robust and so ancient that it has been metabolizing, reproducing, and evolving in darkness for longer than multicellular life has existed on Earth. Both possibilities are real. Both are consistent with current data, and both are, in their own way, staggering. If Europa's ocean is lifeless, it tells us something profound about the origin of life. It tells us that even when you assemble the basic ingredients, water, energy, chemistry, time, life does not necessarily follow. It tells us that whatever happened on Earth to transform dead chemistry into living systems was not an inevitable consequence of the right conditions, but something rarer, something more contingent, something that required a specific set of circumstances that Europa, despite checking many of the same boxes, did not provide. An empty Europa would make Earth more special, more improbable, more alone. If Europa's ocean harbors life, even the simplest microbial life, it transforms everything. It means life is not a fluke. It means the universe generates living systems independently, in environments radically different from the one where we first evolved. It means the probability of life elsewhere, on icy moons, around other gas giants, in subsurface oceans, on rogue planets drifting through interstellar space, in environments we have not yet imagined, is dramatically higher than we currently assume. Either answer changes the human story, and both answers are currently trapped beneath the ice. This is the final and most essential layer of what makes Europa so deeply unsettling. It is not the radiation, though the radiation is lethal. It is not the cold, though the cold is beyond anything in human experience. It is not the ice, though the ice is a barrier unlike any we have ever faced. It is the knowledge, the unbearable, tantalizing, frustrating knowledge that one of the most important questions our species has ever asked may have an answer right now, in real time, in an ocean that exists right now, on a moon we can see right now, and we cannot reach it. Europa is not the loudest moon in the solar system. Io, with its volcanic eruptions and sulfur plumes, holds that distinction. Europa is not the largest. Ganymede is bigger. It is not the most extreme in any single measurable category. It is not the hottest, or the coldest, or the most irradiated, or the most geologically active. It does not hold any record that would make it stand out in a simple ranking of solar system superlatives. What Europa holds is something harder to quantify and harder to dismiss. It holds a sealed environment of extraordinary scientific significance, hidden behind a barrier of extraordinary physical difficulty, in a location of extraordinary hostility, containing the possible answer to a question of extraordinary consequence. The scariest places in space are not always the ones that burn. They are not the ones that crush or irradiate or tear apart with gravitational violence. The universe has plenty of those, and they are comprehensible in their danger. You can see a star explode. You can measure the radiation from a magnetar. You can calculate the tidal forces near a black hole. The violence is visible, quantifiable, and in a strange way, manageable, because you know exactly what you are dealing with. Europa offers something different. It offers silence. It offers a smooth, pale, cracked surface that reflects sunlight quietly back into space and gives almost nothing away. It offers an interior that we can infer but cannot observe. It offers a question that we can ask but cannot answer. And it offers the persistent, unshakable feeling that beneath all that ice, in all that darkness, in all that pressure, something may be there. Not something dramatic, not something that would announce itself. Something quiet, something microbial, something alive, or nothing, nothing at all. Just water and salt and rock and darkness, stretching on forever in every direction, empty and still and ancient and cold. We do not know which. And that is the thing about Europa that will not let you go once you truly understand it. The uncertainty is not a gap in our knowledge that will be filled in by the next press release or the next flyby image. It is a structural feature of our relationship with this moon. Europa exists at the precise intersection of profound importance and profound inaccessibility. It sits in the exact spot where what we need to know and what we are able to learn do not overlap. And it will remain there, orbiting Jupiter every 3.5 days, its ice shifting slowly, its ocean dark and hidden, its secrets intact, for as long as the seal holds. For as long as we lack the means to open it, somewhere beneath 18 miles of ice, 600 million miles from the nearest human being, in a darkness so total that the concept of light has no meaning. There is an ocean. It has been there for billions of years. It may contain nothing more than salt and water and stone, or it may contain the answer to the oldest question biology has ever asked. Europa does not care which. Europa does not know we are watching. It simply continues, orbit after orbit, silent and sealed and profoundly, immovably patient, holding whatever it holds beneath that ice. Waiting for no one, answering to nothing. The quietest, most closed, most unsettling place any human being has ever had reason to think about. And in the darkness beneath the shell, if anything is there, it does not know we are looking for it either. It has never seen a star. It has never felt sunlight. It has existed, if it exists at all, in a world defined entirely by water and chemistry and pressure and time. It would have no concept of a surface, no concept of a sky, no concept of the ice above, or the gas giant beyond, or the distant yellow star whose light has never reached it. If something lives in Europa's ocean, it lives in the most complete isolation the solar system can provide, sealed beneath the ice, orbiting a planet whose radiation scours the surface above. Drifting through the outer solar system in the cold and the dark, 500 million miles from Earth, unknown, unreached, and possibly unknowable for generations to come. That is why Europa may be the scariest moon in space, not because of what it shows, because of what it hides.